So the next paper is called CPA, Cyber Physical Augmentation for Vibration Sensing in Autonomous Retail. It explores a new way for customer product interactions using vibrations. I can't wait to hear it out. Yu Zhang from University of California, Merced, he will be presenting this paper. Yu Zhang is a second-year PhD student at UC Merced. His research interests lie in multimodal human sensing and causal discovery in multimodal sensing data. He's also looking for summer intern opportunity. So if you are looking for an efficient PhD student, please talk to him.
Thanks for the introduction. Hello, everyone. My name is Yu Zhang, and I'm a second-year PhD student at UC Merced. I'm really glad to introduce our work, CPA, Cyber Physical Augmentation for Vibration Sensing in Autonomous Retail. This work is collaborated with Carlos Ruiz, Shubham Rahul, and Shi Jiapen. This is a collaboration between UC Merced and the IFI company. So in the last few years, the number of autonomous retail stores keeps exponentially increase. And this number is projected to be 10,000 by 2024. The stockout problem in traditional store caused a $93 billion annual loss in North America. And the long waiting time for checkout line leads to the customer cancel shopping trip, which caused $37 billion loss. Compared with the traditional retail store, the autonomous retail can decrease this loss and improve the shopping experience of customers. So this good features is built upon a good customer product event detection. There are multiple systems have been explored in autonomous retail, including vision, load, and RFID-based methods. We compare each method from three aspects: accuracy, cost, and effort to atrophy the traditional stores. The vision-based method is commonly used in autonomous retail store because it's easy to retrofit and relatively low cost. But the accuracy drops for small items because of the line of sight. That's why people explore the load and RFID sensors. These modalities can achieve a higher accuracy but require dense deployment, which causes a cost and difficult for retrofit. So we summarize the research question as how to achieve an accurate and low-cost customer product interaction event detection with minimum effort to retrofit traditional store. Let's take a look at what happens when a customer picks up a product from a shelf. The load of the product causes a displacement of the shelf. And when the customer picks up the product, the shelf recovers to the original position while causing vibration. This vibration signal can be used to infer this event. So we put a sensor on the shelf and put down a few sensors. Here's the result. So we can observe that the put down event can induce a strong vibration on the shelf. And on the other hand, the pickup event induced signal is weaker than the put down event, but we still can see it easily. In summary, we can detect the pickup and put down events via the vibration signal. An intuitive solution is to deploy one sensor on each shelf to monitor it. However, this will lead to a dense deployment, which increases the cost and difficult to retrofit. So we wanted to do better by further reducing the sensor required to monitor multiple shelves from a single point. One good property of vibration signal is that it travels far in solid medium. So we place one sensor on the back panel to cover all the shelves. Here's a result. And we can see that the amplitude of the put-down event drops a lot compared to the dense deployment. And we cannot see any pickup event anymore. So what happens to the vibration we see before? In the single point configuration, the vibration propagates through the shelf to the back panel. First, the signal energy dissipates significantly at the junction to the back panel due to the loose connection between them. And second, the rest of the energy exits the back panel in the direction that is horizontal to the back panel, which is difficult to vibrate. So taking this piece of paper as an example, if we excite it horizontally, it's really hard to bend it in this direction. However, we can easily to bend it and generate vibration in this vertical direction. Yeah, so if we can excite the panel vertically and create a tight junction connection, it would allow the vibration propagates better. So based on this observation, we propose a structure that augments the signal from two aspects. First, it enhances the connection between the shelf and the back panel for better signal propagation paths. And second, this 90-degree arc design changed the vibration wave direction so that the event vibration can excite the back panel vertically. So to verify our design, we 3D printed the arc structure and install it to the shelf. And here's the signal for pickup and put-down events with this arc structure installed. We can observe that put-down and pickup events for Pepsi and Purell now. But for the very light-weighted products, such as the candy bar, we can only observe the put-down, but not the pickup. So our second challenge is to detect the light-weighted product events. Compared to the Pepsi-induced vibration, which is very clear in the time domain signal on the left. And the pickup event for candy bar has very low signal-to-noise ratio. That is almost not observable. Thus, traditional energy-based event detection wouldn't be able to detect it. So we further take a look at the frequency domain, and we observe that the signal from heavy product and light product, they have some similarity in the frequency domain, which is distinguishable from the noise signals. We are wondering, can we use this detection of heavy products, which we are certain about, to help with the detection of the uncertain signal from light products? So we propose a cyber augmentation solution. We first use the threshold-based algorithm to detect the events, and we will be able to detect the events from heavy items that we are certain about. Then we train a supervised classifier to distinguish these events of high certainty and the noise signals. Finally, we use this classifier to distinguish the light product event from the noise, which we are less certain about. In this way, we augment the threshold-based event detection algorithm. So put things together, we built our cyber-physical augmentation framework upon the traditional sensing system, where the vibration signal first are captured by the sensors, and then the threshold-based event detection algorithm to detect event from noise. The physical augmentation occurs before the signal acquisition at the sensor, where we use the arc structure to augment the signal propagation path for better event detection. The cyber augmentation occurs after the event detection, where we leverage the detected events with high certainty as labels to train a classifier to distinguish these uncertain events. We conducted a real-world experiment to evaluate the performance of CPA. We selected 4 products commonly seen in retail store. The weight ranges from 20 grams to 220 grams. We investigate 3 shelves on a gondola, as shown on the right-hand side. We collected the product put-down and pick-up vibration data with and without augmentation. The circle with cross shows the location where the pickup and put down occurs. For each product, we put down and pick up for 10 times in each shelf. Note that there's no event detection label data needed in our system. For the cyber augmentation, we use a kernel-based support vector machine as classifier model. This is the performance of the pickup event detection. The x-axis is the production weight. The y-axis is the F1 score of the event detection. The green bar shows the performance of our method with both cyber and physical augmentation. The dark blue bar and light blue bar shows the performance when we only use physical augmentation and only cyber augmentation respectively. The red bar shows the result without any augmentation. So for the product whose weight is not larger than 68 grams, CPA achieves the best performance, and the non-augmentation one almost missed all the events. On average, CPA achieves 2.9 times improvement. So to summarize, we present a vibration-based single-point sensing system for customer product interaction event detection, and we introduce CPA, a cyber-physical augmentation framework that enhances the signal-to-noise ratio and the detection rate. And we conduct real experiments which demonstrate up to 2.9 times improvement for detection rate of lightweight products. Yeah, thank you. And we also have a demo in the demo session to present this work. So please drop by to our demo. I'm open to any question. Thank you.
Hello, I'm Keno Xu from Peking University, and this is a very fancy idea. And I have a question that, if the shelf is full of other objects, and will the signal change?
Yeah, thanks for the question. Yeah, that's a very good question, and we have a previous paper that focuses on quant analysis, how the load change can change the vibration wave on the different structure. Yeah, okay. So definitely the vibration wave the character will change on the different load. So, but in current stage, we are verify these 2 augmentation strategy. So yeah, in the future work, maybe we can use more powerful more powerful machine learning classifier to handle this part.
And you may need to collect more data?
Oh, yeah, in that way, yes.
Okay, thank you.
Thank you.
The 2.9 times improvement you were showing, was that comparing the single point results with the augmentation?
Yeah, so compared to the only cyber augmentation, only physical augmentation, and non-augmentation, the average, yeah.
Okay, and then do you have any sort of sense for how the accuracy for this method compares to the camera method that you mentioned earlier? Wasn't that accurate?
You mean the accuracy? In this way, in this work, it's more like, consider usually for the autonomous retail, the camera is usually installed in the ceiling, right? So
yeah.
So for the shelf, the upper shelf will block the view. So the pinpoint in this scenario is like I don't, from the camera side, especially for the small items, I can grab it. So the human body and the shelf structure can block the view. So in that way, it's like we are proposed, from the vision side, I don't know whether you are really picking up something or retain something. So it's like, in this work, we are provide complementary information for event detection. Yeah, so in the future, maybe we will, yeah, this work is collaborated with the Wi-Fi company. They are focused on the autonomous retail, and they have some commercial store. Yeah, in the future, we plan to compare with the vision-based algorithm. Yeah.
Thank you.
Thank you.
Hi. Seems like a wild idea. I'd like to see where it goes. But first, I wanted to understand what you meant by autonomous retail, and then maybe I have a follow-up question. So what is meant by autonomous retails?
So the autonomous retail is more like by sensing the human activity, the customer's activity in a retail store. So in that way, you can know who they are. So and what items they pick it up. In that way, it can with this computer system, you can know who comes to the store and grab what product.
So it's like the Amazon Go store, which is popularized?
Yeah.
So in this case, when you kind of change the loading on the shelves or the number of things that are there in the next shelf or the amount of weight that's there or the inter-shelf separation, if it gets changed, you need to recalibrate your algorithms completely. Is that correct?
For the physical augmentation, not necessary. You just it's a physical augmentation. You just install it on the shelf. That's it. But yeah, if you have a different size, you might can change the different installation method. But for the cyber augmentation part, in our evaluation, we didn't manually label any data. We take the event energy-based, threshold-based method reported events as a schedule label to train it. Yeah, so in that way, it's like, for example, you can put our system in the store maybe for 2 days. Then they must, some strong signal might happen at there. So you can take this set of data to train the cyber augmentation model without any effort from human, yeah.
Okay, I'll follow up later. Thank you.
Yeah, thank you.
Hey, very exciting work. I had a couple of questions about the sensor. What material, like what type of sensing are you using for the vibration? Is it piezo or?
Geophone.
Sorry?
Geophone. Geophone sensor.
Okay.
Yeah, okay. It's like, usually it is designed for the geometric, like the earthquake or something, yeah. So,
okay.
Yeah.
All right. And so how are you reading off these values from your sensor?
You mean the hardware?
Yeah, like, no, how are you communicating with the sensor, or how are you reading these?
Yeah. So the principle of the geophone is quite simple. It contains a coil. So if that vibration wave propagates through, it will vibrate the coil. Then it will generate a tiny voltage. You can consider it's a magnet. So it will generate a tiny voltage in the two wire outside the sensor. So what we do is we have an amplifier circuit to amplify this tiny voltage, and then that's it. Yeah.
So no, so are you communicating wirelessly? Because it.
No. We don't have we use wire. Yeah.
Okay.
We don't have,
okay.
Yeah. The sensor it's an analog sensor. Yeah.
Okay. And so it needs a power source as well.
Yeah.
Okay.
Yeah.
Okay. Thank you.
Okay, so thank you for your presentation. So my question is, have you considered to use more kinds of inputs? So for example, like you will have like different kinds of products, right? But they have the same weight, but they will have the same weight. So with the vibration sensor, so how can you like how can you like recognize the difference from them? So to have you talk about use another input like from camera, etc.
Let me clarify your question. So your question is like if there are different type of vibration, or what's?
So,
Yeah.
for example, like we'll have like several products. So you have like different kinds of products, right? It will have like, for example, we will have like 2 cans with the
Okay.
same weight.
Okay. Okay.
Yeah,
oh.
but yeah, how can you just you with the vibration sensor to categorize that? So do
Oh,
you need we
okay.
need more inputs?
Okay, I get your question. It's more like your question is like if I have similar type of product,
Yeah.
how can I do item classification
Yeah,
through the vibration sensor, right?
yeah,
Yeah, that's a really good question.
yeah.
Yeah, if you our prior work is use vibration to do human sensing. We can do human identification and also even recognize what type of shoes different person wear. Yeah.
Yeah.
So in that way, we think we can explore this direction. Try to use vibration sensor to definitely do the different item classification. But for the upper bound, like how similar we can achieve this part is possible. Yeah, but this is the future work we plan to explore. Yeah.
Yeah, thank you very much.
Thank you.